Hello, my name is John Kavanagh. I'm representing Group 5. Today we're going to be discussing the design of a composite spar cap. Our team was tasked with the design of an aircraft's lower spar cap to be made from composite materials. The aircraft's spar consists of an upper and lower spar cap connected by a shear web. This takes the form of an I-beam as depicted in the images shown here. The spar runs the length of the wing and is the main loading member of the aircraft wing. It was required that the spar cap be made from an epoxy matrix and be able to handle the loads and moments shown here. The layout of the spar cap shown on the right has dimensions of 12 by 5 inches with a variable thickness. The thickness, along with the cost and weight, are to be minimized by adjusting the design variables of laminate type, fiber orientation, and fiber volume fraction. Before delving into the design process, we can discuss a few motivations for selecting a composite design. Composites have a number of benefits, such as their high strength-to-weight ratios. While the initial upfront cost of a composite system can be higher, the cost over the lifetime of the system can significantly decrease. The reduced weight can result in increased fuel savings and an increased range for the aircraft. On the other hand, we must also consider some downsides to composites, one of which is the difficulty in determining fatigue damage when compared to traditional metal systems. The design process utilized the assumptions of lamination theory, used a safety factor of 1.5, as this was a standard in the aerospace industry. This safety factor resulted in the loads and moments shown here. We used laminator software, which takes in loads and moments as well as material properties and determines the stresses and strains in each lamina. First, the team chose 4831 epoxy resin for the matrix. We then narrowed down the fiber based on the criteria of compatibility with epoxy and usage in the aerospace industry. This left us with the options of Kevlar 49 and E-glass and 2 carbon fibers. In order to identify the design drivers and reduce the number of iterations, the algorithm shown here was used. The algorithm allowed us to best study an individual variable by holding the others constant. It was determined that the order that the variables would be fixed in was ply angle, followed by stacking sequence, and finally fiber volume fraction. After this, we would minimize the thickness of the lamina. The stresses and strains outputted by the software were then compared to failure criteria. It was determined that first ply failure was over-conservative, and the stress and strains were compared to the failure modes shown here, along with Azzi-Sai-Hill theory. To determine the fiber selection, a preliminary design was created with a stacking sequence shown here. A symmetric laminate was chosen to decouple the forces and moments, and a 6 mm laminate thickness was chosen to reduce the number of failures. All fibers were tested at both 60 and 70% volume fraction. The results of the test allowed us to first eliminate the options of E-glass and Kevlar based on their high strains, and finally select T700 due to the lower stresses it experienced. It was determined that the initial stacking sequence was inefficient due to its high number of layers and high laminate thickness. To address this issue, we decided to add more ply angles, and the resulting stacking sequences are shown here, with the final stacking sequence chosen, highlighted in green. Next, the team determined the fiber volume fraction. We studied a range from 40 to 70% fiber volume fraction, as 70 seemed to be the upper limit of commercial production. Ultimately, 40% volume fraction was chosen, as below this resulted in higher failure rates. After fixing all the variables, the team then sought to minimize the lamina thickness. This was done by studying the lamina thickness at 2, 3, 4, and 6 millimeters. The 6 mm lamina thickness had no ply failure, which was over-conservative. The 2 mm lamina thickness had failure of almost every ply. The 3 mm still resulted in a high failure rate. Ultimately, the 4 mm lamina thickness was chosen as it only had a single ply failure at the third layer. The final product was a composite consisting of 4831 epoxy matrix and T700 carbon fiber, with 40% fiber volume thickness and a 4 mm thick lamina. The stacking sequence shown here is a total of 18 layers, resulting in a 72 mm thickness at a cost of $312. The failure sequence shown here begins in the third layer, propagates to the first and fourth through seventh layer, and finally, total failure of the laminate. In conclusion, it was determined the design driver was the stacking sequence. The cost of $312 seems to be well within the range of aircraft components, and the total laminate thickness of 72 mm meets the criteria of the assumptions in lamination theory that the laminate is both thin and wide. This concludes our presentation. Thank you.